Okay, so what's the big takeaway from having gone through looking at this Pascal's triangle? The big takeaway, I claim, is that we're going to be able to use these expressions to work to our advantage in computing the limit associated with our derivative. Because you see, well, what do we want to compute? We don't just want x plus h to the fifth or x plus h to the sixth. We want x plus h to the nth. What's that going to look like? Well, you can see from all of the terms, all of the rows, the numbers in the rows of Pascal's triangle, you always start with a 1. So this is always going to start with x to the n. And what follows? Note, x to the second followed with a 2xh, x to the third followed by a 3x squared h, x plus h to the fourth followed by a 4x cubed h. If you look at the numbers that follow, they keep account of what row you're in. Row 1 followed with a 1, row 2 followed with a 2, row 3 followed with a 3, row 4 followed with a 4, and so on. So if we're multiplying to the nth power, we're going to follow by an n times x to the n minus 1 h. There are going to be other terms as well, but what I want you to notice is, of all the terms that follow after this term, all of them are going to include an h squared, because the first term involves no h's, the second term involves one h, the third term and all terms following have an h squared. So I honestly am not even going to care about what that dot 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 is. As you'll see, the fact that it involves an h squared gives us everything that we need. So let me put this in a box, because that formula right here for x plus h to the nth power is going to be extremely valuable to us. And where's it going to be valuable? It's going to be valuable in computing the derivative. So we want to compute the derivative of, recall, x to the nth power. And well, to do this, we needed to find x plus h to the n. We've got a formula for that. Let's use it. So here, we're taking the limit as h approaches 0 of x to the n plus n x to the n minus 1 h plus h squared times whatever the h squared is times, minus the x to the n over h. So all we've done is taken our x to the h to the nth, x plus h to the nth power and rewritten it in our parentheses here. This parenthesis corresponds to that multiplication. It's precisely what we worked out from Pascal's triangle. And now, check out the expression that follows. You've got this whole thing. X squared plus something minus x squared. Or x to the third plus something minus x cubed. X to the n plus something minus x to the n. I don't know what x to the n is, but I know if I added it and I subtract it away, those things cancel. And I know what's left. Look at these two terms. They both involve h. So if I factor out that h, the first term is going to be n x to the n minus 1, and factoring out an h from what's left is now h times whatever follows. Because it was h squared, take one of those h's away, you have a single h remaining, and now we've got an expression like so, which, taking the limit for the derivative, the h in the denominator presents the problem from the get-go. But notice what we've got now. Since we factored out the h, we have an h upstairs and an h downstairs. That cancels. And when that cancels, we're left with just the expression n x to the n minus 1 plus h times something. And now remember, we knew that something was whatever it was. We really didn't care what it was, and I told you it wasn't going to come into play. And in fact, it didn't, because note, the h is going to 0, so whatever this thing is going to be multiplied by 0. So this thing goes to 0, and the only thing that's left, the h's have canceled, the h times whatever that thing is now 0. The only thing that's left is n, x to the n minus 1. And now we've got a formula for the derivative of x to the n. It's n times x to the n minus 1.